Yeah, thank you. Yeah, it's very nice to be back to Reading. I'm sorry that I couldn't come for longer, but I organized a workshop myself earlier this week, so I only could come last night. Anyway, so I changed the title. I mean, it's I think in the booklet it still says scored generative models, but that would have been a bit of a track of the conference anyway. So, and then I saw Dan's title, and so I thought I have to follow up on this because it's quite nicely linked, I think, to what you just said. So basically, I will talk about exactly the same problem that Dan talked, and I will just introduce a different kind of approach to the same problem of nudging. To keep things simple, I will just look at a single data assimilation cycle in what you described in your previous talk. So, and I will keep everything time continuous. So there's a time continuous model, pretty much exactly as you saw it in Dan's talk. There's a drift term and a noise term. For simplicity here, it's just a scalar diffusion constant, which can be a bit more complicated. And then basically, the setting is, as I said here, I will just look at a single cycle, because basically after that, once you can do a single cycle, you can do plenty of cycles if things go well. So basically, a single cycle starts with some initial distribution, which basically comes from your last data assimilation cycle. So meteorologists would call that the last analysis. And then this initial condition is propagated forward by your process, the SDE in this case. And then at capital T here, you get an observation. And so basically, this initial condition is being transported forward to time T, and then it becomes the prior for your data assimilation step when you think Bayesian. Here in this simple setting, I will assume that, just to keep the discussion simple, that the forward model H, which maps the state to the data, is linear. And then you have Gaussian noise, very much like what it was in Dan's talk. And then you do a Bayesian inference step, and that gives you the distribution at capital T, C in the data, and that's again called the analysis in metrology. And then the next cycle can start. And the goal, of course, here is to infer the reference state, which I denote by dagger. So dagger is the truth, like the true state of the atmosphere, and Y dagger is the thing you observe, and that's it. So that's the setting, but it's exactly the same thing as in Dan's talk. And so we want to do Monte Carlo type implementations, ensemble-based methods for such scenarios. Now, on a bit more abstract level, again, just following the standard notation. So the SDE has, if it comes, a Fokker-Planck equation that describes the actual evolution of the densities. So that's coming from the SDE. That tells you basically how the initial distribution P naught is transformed into the distribution at PT, which is the prior. So that's just model driven. And then the likelihood, the Bayesian inference step is at the bottom of this transparency. You should all, I guess you all in this room have seen this. It's just, as I said, the standard Bayesian inference step. So basically you have to intertwine this sort of prediction step with the data assimilation step. And the problem is that the PT, your prior, the model, the prediction of your model can be quite off from your observations. That's when it becomes challenging. And so the posterior is not necessarily close to your prior, which comes from the prediction of the model. And that's where this whole nudging idea comes in. I mean, can we sort of steer stuff already in the right direction in those scenarios? And so here's an example just to illustrate to you the point. It's very contrived. It's a two-dimensional example, and it's a nonlinear Ornstein-Uhlenbeck process. So the drift is actually a gradient of some potential, and then you have some noise. By the way, interrupt me when there's a question or something is unclear. So we don't have to split it into 20 minutes talking me and then 10 minutes questions. And the potential is constructed in a particular way. So the blue part is sort of a confining type, where the dynamics in 2D basically is confined more or less to a parabola. And so that makes the thing nonlinear. And then there's the second part, the red part in the dynamics, which is a bistable potential. So basically, when x1 is positive, is a stable, basically well, and so the particles will giggle around in that well for a long time. And then you have rare transitions over to the left side in x1. And so that makes the thing difficult to predict when you have one of those rare transitions. And the setting is as described there, but it's probably better to illustrate with a picture. So the green line is a parabola where the dynamic sits on. So it's two-dimensional state space, so x1, x2. And then, as I said, in the x1 direction, you have to think of a bimodal potential. So I like this. And so I start with positive, I mean, my ensemble, my prior time 0, my last analysis told me the system is on the right? So it's on the right side. And so there's a bit of spread, but everything is there. Now you do a Monte Carlo simulation of your STE, so a particle filter essentially, without the filtering yet. And so the blue ones, the blue dots or crosses are the initial ones, and you can hardly see them because they're superimposed with very much what you see after a 1 unit of time. The particles have moved around, but they stay in that well. So this is for 1,000 particles. None of the particles has moved over to the other side. If I would have used 10,000 particles, actually some of the particles would have hopped over to the left. But in this scenario, it hasn't happened. So all the particles believe happily sitting in this one well. And now, when you now do particle filter, the Bayesian inference step, you basically lost, right? Because the best particle, is that the, which one is the, oh, here, oops. Well, the best particle would be this. I mean, and you now observe, okay, I should say you observe that actually one of these rare transitions has happened. So the truth actually has hopped over to the other side, right? And you actually only observe the X component. So the true value is this, but you only observe the X component of it. Of course, knowing that you're on a parabola, you can easily construct then the Y value, the second value, but we don't know this, right? So this is, I mean, not the data assimilation system doesn't know that. So anyway, so the best guess would be this, but it's still way off. So this particle would get all the weights, and any jittering, anything would not help you with this, right? So that at that point, the particle filter is essentially derailed. Now, what is the ENKF doing? The ENKF is doing much better. So the ENKF, in a way, uses linear regression. So it will actually pull all the particles. So this is the ensemble you get from the ENKF doing this, right? So it pulls it obviously in the right direction, but because it does linear regression, it just sees it on this line, so it moves everything up there. So the X component, X1 component is very well recovered by an ENKF, but the second component is way off because it doesn't see the curvature, right? So the nonlinearity of the dynamics is lost, or actually the distribution of the nonlinear distribution of it is lost, right? So you get completely unphysical states, very quick adjustment processes, and so hell breaks loose essentially. So none of the two methods in this particular admit a very contrived situation, it doesn't work, right? And so it's clear you have to do something to steer the particles in the right direction. Now, if you were to do variational data assimilation on that, so the 40 var, it would get it right, I believe. I mean, I haven't implemented it, but I'm pretty sure it would get it right, because then you're actually looking at the whole time window and you're trying to adjust. I mean, 40 var, of course, would only in the basic setting would only give you a single trajectory. So you would start with your best initial estimate at time 0, and then you would solve this variational problem, and but you encode it over the whole window, including the dynamics and everything. So it would be actually, in this case, would be a weak form of 40 var, and I'm pretty sure it would have covered. So, but we would like to move to ensemble methods and no derivatives, no minimization, no nothing. So let's see how to do this. So the idea, of course, we borrow from control theory or from 4D-War, right? So 4D-War is sort of has a control flavor to it. So in this time continuous setting, you can think, okay, and that's again very much in line with what Dan talked about. You want to find sort of an additional drift term that gets you in the right position, but doesn't violate the statistics of your problem. That's the key, right? You could, of course, do anything, G, but you want to get the right G, so that it also complies with the statistics. There are basically two well-known mathematical scenarios in which you can do this. So the one that's associated with 4D-War is smoothing. So basically, it's well understood that basically, I mean, we're talking here about filtering, right? So we predict and then we adjust the distribution at capital T, times capital T, according to the data. But of course, you can adjust all the paths. You can reweight not only the final condition, but you can reweight all the paths that led from the initial time to time capital T, according to your SDE. And it's called a smoothing distribution. Now, basically, you can find a control law G such that this modified SDE has that this random variable here has distribution exactly according to this smoothing distribution, right? And that's a well understood methodology. And it's very, I mean, 4D-War, weak constraint 4D-War is doing nothing else than finding the map estimator according to the distribution, not the whole distribution. But there's of course there's a slight problem with this still because at time 0, it doesn't agree with the analysis from your last data simulation. It should not, because obviously the data at the future, so to speak, informs the past at that point, right? So there's still a sort of resampling step involved if you think of particle filters. But of course, generally speaking, it works much, much better if you solve that problem. And then there's sort of one step further when you say, okay, yes, I really want to go from my last analysis to the next analysis directly, and also want to find a control law G. And that's possible. It's not unique. So you introduce some cost function. It's the Kullback-Leibler divergence between the two processes, essentially. And it's called a Schrödinger bridge problem, or it's a generalization of a famous problem that first posed by Schrödinger. And so it becomes a boundary value problem. So you prescribe the two distributions, and then you want to find the control term that exactly bridges these two. So that's the holy grail. That would be the holy grail of data assimilation. If you were able to do this at the end, I mean, basically, we should all just do this, I believe. Nothing else. A little bit of catch to this. So the catch is, of course, in the computations and practical implementation of the whole thing, as always, right? So mathematicians dream up beautiful things, and then reality hits you at some point. The smoothing problem, basically, I mean, in many implementations of this, one way is sort of forward-backward SDE formulation. So you simulate forward, and then you have to simulate a backward SDE. That's actually not too bad. I mean, with particles, and it's a well-known concept in sequential Monte Carlo methods called the so-called optimal proposal, even though I think it's actually not optimal, but you know, in a sort of, I mean, you have to specify what optimality means. But anyway, so this is a well-understood concept again, especially if you think of time discrete Monte Carlo, sequential Monte Carlo methods. And in principle, it's doable. And as I said, 4D-Var is doing something very closely related to this. But if you think of Monte Carlo method, then you still basically have to do resampling because this mismatch of the sort of analysis, the new analysis at time 0 with the old analysis. But typically, especially if you have SDs, the difference between the distance between these two is smaller than at final time. So there's typically quite a gain if you manage to implement this in a sequential Monte Carlo method. Now, Schrödinger is basically just kicking the whole system a little bit further, because one of the way you can solve Schrödinger problems, if you're familiar with Schrödinger problems, is a synchron iteration. And the single iteration is basically a continuation of smoothing. So you basically keep, instead of forward, backward doing it once, and then you have the smoothing solution. So you get the G out of this process. You keep going forward, backward, till it converges, and you really hit the two distributions. And so you already realize that Schrödinger problems are much harder to implement numerically. In fact, it's a very active area of research because Schrödinger bridge problems, I mean, like optimal transportation and things like this. I mean, Schrödinger problems are a generalization of optimal transport problems, are tremendously, notoriously difficult to solve. So very important and useful, though. Sure. I mean, I love it, right? I mean, it's beautiful. I mean, but as I said, numerically, it's a bit of a nightmare, right? So I'm not sure if any of the meteorological offices will move to Schrödinger bridges so soon. I mean, computationally. I just wanted to make a plan for optimal transport. Oh yes, yes. I mean, yes. We all. I mean. Yeah, so there are beautiful connections also to resampling schemes in sequential Monte Carlo to transport. Yeah, but the whole theory is beautiful. I totally agree. And basically, optimal transport arises as Schrödinger problems when you eliminate diffusion, so everything becomes deterministic. So in fact, the relaxation to Schrödinger helps you a little bit. I mean, the numeric becomes a little bit easier. Generally speaking, it's sort of a relaxation of optimal transport. But the real catch with this whole thing is that, you know, even if you were to do this very efficiently, the big problem is sort of all this assumes that you already know what the analysis at time capital T is in a way, or you have already a good approximation, because basically you start, it's like a sort of a shooting method or sort of, and you have to have a good first go at it, right? Now, the example I showed you, there wasn't a first good go at it at all, right? And then you don't have a good approximation of your second target distribution, but Schrödinger sort of assumes that you have this. So there's a bit of, you're biting yourself in the tail situation, or chicken and egg, or whatever you want to call it. So again, methodologically, I think there's a clear target. I believe what we should go for, but how to do it. So now, so here I said there's this optimality, and again that helps you a lot. I mean, it's a convex minimization problem. It's beautiful mathematically, but maybe we'll have to give up on this. But before we give up on it, let me just give you a little bit of references. So particle filters, a wonderful book by Nicolas Chapon. Sort of particle filters in very high dimensions. There's an overview now a few years ago. If you want to know about Schrödinger and various bridges, optimal transportation, there's a very nice SciM review article. I really recommend this. And then I sort of myself wrote something on, I said, well, data assimilation should really be Schrödinger. And that's also a few years ago. And then the talk, if you want to read the details, because it's definitely going to be very fast now, it's an archive paper, which was just uploaded a few weeks ago. Okay, so that goes back to something I've been doing for many years, pretty embarrassing now. Basically homotopy, which is nudging, right? Nudging continuous time, I call it a homotopy, but it's nudging. And so the idea is to not work directly with the processes, but to go up on the level of densities and then just say, okay, I mean, I want to solve, I want to go from one distribution to another one. There are many ways to do this, right? So, and you just write down sort of a continuous deformation from one distribution to another. And in this context here, the best deformation, I mean, I at the moment can come up with is the following. So basically this distribution, PT, is the distribution, the marginal distribution of your stochastic process, of your model, underlying model at time t. So that's what the free dynamics is doing. And then I'm tilting this by the likelihood, the data likelihood. L is the data likelihood, log likelihood, negative log likelihood, right? So this is the data. And I bring this in right away, pretty much as, again, like Dan did, in a different, slightly different setting. And it's weighted by t, lowercase t. So at time 0, nothing happens. And then as t goes up to capital T, you realize this product is then PA capital T. So it bridges this simple formula, bridges the analysis at time 0, which is just this here, because this is then just 1, with the analysis at time capital T, because then this factor becomes 1, and then this has also moved on to capital T, and so everything's perfect. All right. So that's easy peasy. Right? And it's an old idea if this is not changing. This homotopy idea has been explored in Bayesian inference, for example, when you say the parameters underneath are not changing. So the only thing that's really new here that I say I can combine this with an underlying stochastic process. Okay, here we go. So now we have to find a process, a stochastic process that does it for us. That's the only open challenge. And so the way we can solve it is the following. So here again is the underlying stochastic process that's associated with this. So that's what we got. And now we modify this model by adding 2 terms. And basically, what you need to do mathematically is to look at the Fokker-Planck equation that comes with this. The Fokker-Planck with this I wrote down earlier. So, but you can also easily then adjust it to this Fokker-Planck equation. And then just make sure that the density evolution that comes out of this Fokker-Planck equation satisfies exactly this condition, provided that this density satisfies the Fokker-Planck equation of that process. So it's just a little bit of algebra, bit of differentiation. Now, why I wrote it down like this, because basically when you do this analysis, you find there's immediately one drift term popping out of the analysis. Straight to your eyes, and that's this one. And it's quite nice because basically it's saying this is the gradient of the log likelihood function. So this is a term that whatever happens nudges you towards the observation. It depends on the noise. So if the model has no noise, then that term disappears. By the way, this all works without noise, right? This is, I mean, I added noise here, but it doesn't rely on Girzanov, like in Dan's talk, right? So this all works. But anyway, so the noise really helps you because it sort of, this liberty drives you to the data. And then you have another term, G, that's a bit more fiddly. In fact, if you ever looked at this homotopy stuff, then you're not surprised. There is this G is implicitly defined. Basically, you have to read, I mean, you look at the evolution, the time evolution of your densities, and you have to reinterpret the changes in the density by a drift term. And it's possible. And you get this equation. So G, this is basically the Liouville part. That tells you how the density changes given a G. And that change has to mimic what the density by your homotopy ansatz is meant to do. And so you get 2 things. You get, again, the negative log likelihood function. So that's basically what you would get with standard nudging approaches or so. But now there's dynamics. So you also get the derivative, the change of L in the direction basically of your evolution system, which is also maybe not surprising that somehow the G has to compensate for things that the dynamics does to your distributions. So this is a sort of directional derivative. So it looks a bit ugly, right? But in principle, you can now say, okay, I can solve for this G. So I have an elliptic problem, I have to solve for it. So, okay, so I'll only say, okay, fine. I mean, but then, you know, the Kalman filter comes to your rescue. Because what is the Kalman filter essentially doing in this perspective? If I would not have dynamics underneath, you can derive the Kalman filter from this whole picture, basically dropping the red part. And then making an ansatz that this G is linear in X. So you're basically saying, I want the G to be linear. That's the Kalman filter, essentially. It's a linear, it's a best unbiased linear estimator or whatever way you want to look at it, but it's basically a linear ansatz. And you make this and then you project basically down onto this linear ansatz. And then you get the following terms. Pretty messy, but quite interesting. So the blue part here leads to something, it's a gain and basic innovation. So it's exactly what you get in an ensemble Kalman filter. This is now a time continuous version of the ensemble Kalman filter. So you think of the square root filter, the ensemble Kalman square root filter, but in continuous time. So that's what you get. And then you get something that comes from this, which actually doesn't involve the data. So this involves the data, that doesn't involve the data, but it's scaled by t. But you see, these are covariance matrices. So this is the covariance matrix in state space. This is the covariance matrix between X and F, the drift term, et cetera, et cetera. So the sigmas are all covariance matrices, which you can estimate empirically. The gain also is a bit messy. So you have the standard, basically covariance term, and then the multiplication by the, that's why I assume the linear forward operator can pull it out to make it easier. Otherwise, you would get correlations here between X and H. And so that part, again, the blue part is what you would expect from a Kalman filter as it comes. And the red stuff is additional. And it's actually quite interesting because there are some terms that are actually stabilizing, some terms are destabilizing. So how am I doing with time? All right. Please start ask questions so I can talk longer here. Because I have quite a few examples now but maybe you can just ask me, right? So this is for just what happens for diffusion. And as I said, are interesting things because there are some stabilizing terms. But here's, I mean, you see basically this example, let me at least go for this here. So the prior is a Gaussian mean 0, variance 1. It's just drift. So the posterior would be mean 0, variance equal to 2. So it would be way up there. But the data contracts down everything. So the variance becomes very small and the mean is 1. And so you see this homotopy thing has to do a lot of work. Of course, it's just 1D, so it's not. And but you see it starts at 0 and the mean gets up to the right value, 9.96. The variance starts at 1, it goes down instead of going up. So it does the right thing. I have another example, let's skip it. So let's look at this example here because what is it doing here? That was the nonlinear example I had. And now here is what this nudging stuff does. Or homotopy. So here's your initial distribution, and here's the final point of clouds with this homotopy. And actually, you see a lot of work is done very early on. So I was actually, when I first implemented this method, I was expecting that this homotopy would not do anything for a long time, and then suddenly it would start kicking in very just close to the target. But it's apparently, you see at 0.02, this not much has happened, and basically I initialized strictly on the parabola, so it gets giggled around, but you already see some particles get pushed. And then 0.2, actually the particles are already almost moved over. All of them have been pushed over 0.4. 0.8, you basically there. And then the final cloud of points is there. So it does it. And that basically was an implementation of this formulation here with all the terms, as I said, approximated as you would do in an ensemble Kalman filter. The time stepping, I used basically what an ensemble Kalman filter would suggest. I mean, the Euler method is not ideal for this. But basically the Kalman updates suggest you really good time stepping method. And pretty much that's the story. So basically what I've been talking about is looking at this from a control perspective and starting from generalizing this well-known homotopy ansatz to when there's an interesting underlying dynamics and not just 0. It solves the Schrödinger problem in a way, but in a suboptimal way. Because the way I prescribed the bridge was just ad hoc, so there might be better ways of prescribing it. that gets you closer to the Schrödinger solution. Of course, you could also use it as an initial guess for the Schrödinger iteration. So that would resolve this issue that you first need a good guess to get Schrödinger to kick in. I'm not sure what you really would get from that, but that's an open thing, maybe also interesting. Now I talked about how to implement this using this constant gain approximation, back to the Schrödinger. So that introduces biases, and it's not, like what Dan talked about it, where you can prove rigorously, asymptotically, everything will do the right thing. But on the other hand, we know in metrology, robustness is a big issue, and we can only afford a reasonable size of ensemble sizes. Can be extended to nonlinear forward. Basically, it's the same good old trick. I mean, you replace correlations by, you don't take derivatives, but you compute cross correlations. This is all for L2 loss functions, which in metrology, of course, fine. Of course, there are many other applications where the L is not an L2 loss function. I've been also curious if there are applications to reinforcement learning. Yeah, I didn't say too much about numerical implementations. I mean, well, I said a little bit. I mean, I'm basically following the ENKF. So I didn't use any inflation or localization and all these tricks we need to think about. But I'm pretty sure that, at least localization should be. I mean, basically, you end up with the same matrices that you also get in the standard ENKF. And so this whole concept of localization should be applicable, at least in metrological applications. So. And then, of course, there's this big issue, of course, long-term stability. So I showed you just sort of a single cycle, and we're now working on doing it for the Lorentz system and sort of things. Okay, so that's it for my end, and thank you very much for listening.
Slightly graph. So you started off by saying if it was deterministic, 4D bar is essentially a good approach because it has this smoothing property. And then when you moved on to the stochastic case, you said you really wanted a sort of update or nudging, which was like an NKF update using common gain. So I'm just thinking, so if you so the thing you didn't have in the 4D bar case was just deterministic. If you have an ensemble of 4D bars, that in a sense it seems to do both jobs at once. So what's the right idea?
Yeah, so if you would run an ensemble of 4, so that should basically deliver you. It solves the smoothing problem, right? So it solves this or approximates the problem I wrote down here, right? So that's what it's meant to do. So so you can I mean, so that basically that's if you're happy with 4D var, with an ensemble of 4D vars, then I guess you basically do this implicitly. You also compute. I mean, this is a weak constraint form, but I mean, if you do it deterministically, then you're only adjusting the initial conditions. And in the weak constraint, then you would see this term coming in, really. I mean, you could read it off in a way. Yeah.
So the usual case in the sort of discussion, the same sort of method you described, are essentially already assuming simple structure. The nudging, if you like, is all done using some common gain formula to really assume things linear and Gaussian. And you might have something extremely non-linear. So the particle filter is always sort of sold as a not very practical but possible way of dealing with things which are non-linear and non-Gaussian. So what you're sort of describing doesn't really say that you're still really doing the linear Gaussian case in this, but then stochastic rather than this setup.
Yeah, so so the question is, I mean, how non-Gaussian is it really, right? So basically by this nudging, you always stay close. I mean, at least in this setting, basically locally, you're always very Gaussian. But where the problem arises is basically if you try to do this globally, like in this example, and then there's no rescue to the ENKF in this particular case. But if you do it in each step and you go along this manifold, everywhere locally, it's basically linear. So that in that case, it helps. I mean, of course, yeah, if you have horrendously nonlinear observation operators and the distributions are horrendously nonlinear, then, but I mean, of course, I just said I make a constant gain approximation. But of course, if you have many if you can afford many particles, you can try to solve this numerically using the diffusion maps. So there are numerical techniques that you can directly, using particles, infer the G, also if G is not, you don't make any further assumptions on G. But yes, we can, you can implement this, and then you get a particle filter which would do the right thing. But it definitely requires structure or some very large ensembles or some structure that there's something, maybe you can confine it to some lower dimensional spaces which are highly non-Gaussian.
And I'm sensing that my pre-conception was you really had to have an extremely large ensemble to fill the phase space before you really think of it.
Yeah.
I think you'll agree with that.
Yes.
So we have a particular example which is limited area forecasts constrained by a large scale forecast, and the large scale constraint force small scale bits to be within right phase space. Now you might be able to use possible nonlinear.
Right. Yes. Yes. But
it might be seriously more practical application.
Yes, I think if you can confine it to yes, and yes, no, I totally agree. Nothing else to say. Yeah.
So your example is as long as just concentrate on position low but if you have also that is spread, then exactly what you need to do is cluster particles. And in each cluster you localize the signal. And what's the gain in that local
Yeah, I'm not sure about it, but basically, there are various ways. There are many ways to approximate it. You can, for example, assume that you can approximate the density very well by Gaussian mixture, right? Then you can actually write down again evolution equations. So then you can sort of find a G that does it for you. But then so you have to be able to then say, like if you have a forecast that's really bimodal, then you can fit sort of two Gaussians to it. So you have a Gaussian mixture, and then you don't work any longer with a Gaussian. For each mixture then component, you do a Kalman, but you also have to have a contribution that sort of talks about the exchange between the two Gaussian mixtures, components. So it's possible. It's a matter to making this robust numerically in real applications. And so, yeah.
Actually, I guess the workshop's partly on prediction, right? So that's the problem where you're either not interested in observation, you're interested in so there are ways to, and then in there, of course, you would like to maybe
Yeah. Basically, that's why I talked about this reinforcement learning. It's sort of a little bit similar. So basically, the L can be any cost function. So you could say, I really want to observe a storm, right? So you somehow have a cost function that increases the chances of seeing the storm. You would have to give me that. Then I could put this in here, and then I could say, that gives you a way, just one way to bridge scenarios, possible scenarios, how that could arise under such a tilting. Of course, then maybe the question is a little bit, is this then a good bridging assumption to bring this in? But it's a first guess, right? You can do many other things, but it certainly would be one way. And then you could also say, well, trying to solve the Schrödinger bridge problem, which would say, which is the one scenario that gets you there with the least Kullback-Leibler divergence to what the nature would try to do. Like the free process would try to do. But yes, you can play with scenarios and try to, how do I get there? Yeah.
Just a short question. So are you worried about the fact that you get destabilizing corrections? And if you are, could this be, this is probably due to the fact that ultimately this is a finite time thing, right? You go up to capital T and that's it. Could you amend this, or what would happen, let's say, if you set up the problem in a way that you reach the target as little t goes to infinity? You could do this, right? You could say, rather than having on the previous slide, rather than having little t there, you just have something depending on little t, which goes to capital T as you send little t to infinity. Right? And if you did that, I mean, potentially those destabilizing terms just disappear.
Well, I'm not sure. I mean, like,
yeah, I'm not sure either.
I mean, I think there's a lot of interesting questions basically come out of this. I mean, what kind of dynamical system is this actually? I mean, what is this doing? I mean, of course, we know it on the level of densities. I mean, everything's perfect and we know exactly what it does. But let's say you think of this now as an independent dynamical system and say, what are the properties of that system as a dynamical system? And then I think this is really interesting because, as I said, it's sort of, if you take no noise and just a drift term, you make it linear, you see actually, so lambda, and it's just the lambda is basically lambda larger, it's unstable, lambda less than 0, it's stable. Now, so basically you see that if lambda is positive, then this is unstable, but this is then by definition always stable. And also this term becomes stable. So then the data assimilation actually definitely only stabilizing the whole thing because the own dynamics is just trying to blow away. So that's good news. But it's interesting, if this is stabilizing, then some of the nudging terms actually trying to push the ensemble away from each other, right? And that also makes sort of sense, right? Because basically, if everything goes, I mean, in this case, the solution all go to 0 because it's just a linear system with equilibrium 0. And then the data is basically, you know, just redundant in a way, but you still want to get the right spread. And so you need some, I mean, intuitive, that's the way I look at it. You need some destabilizing term potentially just to have the spread right, because you don't want to just collapse on the observation. So it's very interesting. I think it's really kind of curious what these systems will do in terms of dynamical systems as an approximation, just as an approximation. Yeah, oh no?
I suppose there is a relationship that gets me going. I don't understand the answer to that question. Say that you have a case where authorities would call an evacuation if the rainfall is above a certain threshold. So how do you put that in your L? Because what you would like to, what the authorities do not want to do is call a false evacuation. So somehow in your L you need to you want the uncertainty of a wrong prediction to be lower. So how would you put that in L? So after a certain threshold you want extra certainty that you don't do the wrong thing. That's really what you want, right? So how would you fold that in?
Well, I guess then you really have to bring in Gilzanov again, right? So you change the measure. So it's just a computational way of getting a more reliable prediction for these sort of rare events. So I'm talking a little bit off my breath here now. But I would say, I would think that you can combine this with what rare event simulation techniques. But maybe I should stop here because before I start talking nonsense.
It's a very important question.
Yeah, sure. No. I mean, as I said, I mean, this is just a few weeks old. So I'm happy to talk to everyone who's interested in these sort of ideas. Say again?
We'll make you responsible.
Oh, for the next wrong prediction of the DWD. Yes, I take all the blame for that. Yes, sure. Yeah. But all I want to say, I mean, you can definitely replace L by another cost function. And then, yes, the matter is how do you interpret this then? I mean, if it's in reinforcement learning, it's pretty clear what you're doing. But like what is there now you just described, I don't know.
Just a remark. It seems to be going back to what Jeroen has been.
Okay, yeah. So yes, I'm happy. Oh, I mean, these ideas are in the air, and it's also Peter Jan has been looking into it. I think it's just a nice way that we have a clean mathematical reference system now. I mean, this PDE system, and then we can start making approximations. So in principle, yeah, so there's a clean background picture now. Yeah.
I didn't really get your comment that the game is stabilized. When the system is stable, and it still remains stable, but
Yeah, I mean, the numerical simulations indicate it's stable. But let's look at this diffusion case here. I mean, now this is the opposite case. No diffusion and just no drift, just diffusion. So then I said you get this, you always get this nudging term where it's not weighted by the ensemble. That nudging term is always there, and it increases linearly in time. And then you have something, and that sees the data. So this should be the y decker here. So it's the same as this here. So this definitely pulls you towards observation. Definitely. Now the second term is more tricky. It's also, that actually looks very much like an ensemble Kalman filter, iteration time thing, the gain here, oops. The gain you would get, but then there's this factor in here, and you see this diffusion-driven term has a negative in front of it. So initially this is dominating, but as t goes up, this can change sign. And then suddenly this term pushes the ensemble away from each other. So this is always stable, but then suddenly this is becoming.
what does it mean that this? Just the fact that the assembly is spread out. Why does this imply that the system?
No, I'm not saying the system is unstable. I'm just saying this is just diffusion. This has a stabilizing effect. And this, if it would just be that, then it would be destabilizing. The question is, what does it all together? And altogether, it seems to be nicely stabilizing.
The
All right.
observations are more uncertain,
So you could say it's a bit of an inflation.
but you're saying the observations are more uncertain, affected by that condition, isn't it?
Yeah, but as I said, it kicks in at a certain time. I mean, initially, it definitely, it also pulls you towards, it pulls the whole ensemble towards the observation. And then at a later time, it sort of says, oh, I push it a little bit away. But this is still definitely from the numerical simulations, and it should, this is all Gaussian, so everything is exact here. That's still contracting stuff. So yeah, so this is a Gaussian case. I mean, this is all perfect here. I mean, this is, I mean, if you start with initial Gaussian distribution, it's just the right thing. So, but yeah, so definitely an interesting question. I mean, we do this really now for nonlinear systems. How does it all behave together? All I'm saying here that to achieve this sort of homotopy, it's not just that you get stabilizing terms, you also get some terms that tend to push you from away from the observations.
Sure that the term at the top can be directed in some directions, but the term at the bottom that can be somewhat destabilizing in other directions.
No. This is really sort of standard nudging, you could say. This is just a standard nudging. Yeah, so you're nudging in the direction of H, right?
Where you don't have the observation.
Yeah, right.
If you don't have observations for some directions, it doesn't mean that the other term would be not existing.
Yeah, so this could be, yes.
It can drive you in completely wrong direction, in directions where you don't have.
Exactly. So if this here, if this matrix, of course, directs stuff in direction that are not in H, and in that direction, it would indeed. Yes, but apparently that's, I mean, as I said, this is just correct for Gaussian case. I mean, at least in the Gaussian case, nothing is happening. But I agree. I mean, that's why I'm saying it's going to be. Yeah, but I agree. There's some interesting questions what it does in a nonlinear setting. where it's no longer Gaussian and it's an approximation. What are the stability properties, long time, whatever properties of such systems? Totally agree. Yes. Yeah.
Actually, sort of brings the point about the fact that you might know every aspect of one, not necessarily because it's interesting that in Dan's case, this drift term is constrained to certain participant. That's it. That's the whole thing. That's because it's a huge point. If you have a frame equation, then there's other aspects. You haven't really talked about it. There's also an area of distribution where people are trying to say follow the dynamics. So this idea that you can constrain the dynamic and just do that by letting the model do something. So that's another kind of angle. Because that's part of the answer too. If the model can sort of, then you one step is you have to look at how things go.
Right. Yeah. No. Of course. Yeah. That's raised an interesting question. I mean, can you build in conservation properties into this, right, or anything else you want to have? Yeah. Open question. Yet another open question, right? Yeah. So, but yeah, it's the same question you have generally with the ENKF. I mean, can you build something into the covariance matrix? Anything linear, yeah, you can build in perfectly. Anything nonlinear, but you can add this, right? I mean, you could add some conservation if you want to as a constraint. Yeah. I don't know. Any on the? No, nothing. Okay. Okay.
If there are none, let's say. There's a short break before lunch, which is going to be on time.
Yeah, so the lunch, we now have 20 minutes, and then the lunch is going to be served not here, but in the Cedars meeting room.
I'll try to pull up a map.
Okay, that's great. We can also just go there.